Good afternoon, everyone. How are you all doing today? Well, that is good. I'm John Mann, Director of Education for Lakeside. And during this week of lecture series, we're exploring the region of the U.S. known as the Great Plains. And today's session is titled Extreme Weather of the Great Plains. We're fortunate to welcome Ross Ellett back to Lakeside. Ross is currently part of Toledo's 13 ABC weather team, where he serves as a weekday morning meteorologist. Ross has personally experienced a variety of different weather settings and challenges in his career and holds the Certified Broadcast Meteorologist designation, the highest professional certification awarded by the American Meteorologist Society. I would ask you to please mute your cell phone ringers if you haven't already, and help me in welcoming Ross Ellett.
Thanks for having me back. It's great to see so many of you guys out here today. And when we were kind of looking months ago at these different topics and talking to different folks weather-wise on what areas of the country we wanted to talk about when it comes to extreme weather and the climate, somehow I ended up with the Great Plains. And the Great Plains, the thing is, when you're talking about extreme weather, it feels like about once every week there's something extreme happening in the Great Plains. So it's a fascinating area of the country to talk about. There really is no other place in the world quite like it on this scale. And extreme weather really is kind of a norm out that way. Through my career, I've worked in a variety of different states. I've been here in Northwest Ohio now since 2012, so it's been 14 years. But I did spend several years in Northwest Arkansas, so kind of on the edge of the plains there, and we were almost on the border there of Oklahoma. We had counties we served in Oklahoma as well. And two of the four extreme weather events that we'll talk about today, I do have some personal reflection on that were very big events, so I'll reflect on that as well. Now I'm going to start off talking about the climate and what makes the Great Plains so extreme and so unique across again, comparing this spot compared to the rest of the world. So we take off starting looking at the climate in general. And so this is a complicated map. There's a lot of different colors, a lot of things happening there into the Rocky Mountains especially, but you basically have a continental, temperate climate, and then you also have an arid, a desert climate. But where all these climates seem to come together is right in the middle of the country. And if you think about it, we really have the desert southwest, but even farther north, you get to areas like Wyoming, and you think of how dry that is. You get on the other side of the Rocky Mountains is weather makers go from west to east generally across the country, and they go over the Rocky Mountains, and they begin to basically lose a lot of that moisture with these weather makers on the front side of the mountains. As they come down on the other side, things dry out and it becomes very dry. And that is really what leads to those big climate zones across a lot of the country, but especially out west. And so you end up with a lot of dry weather, especially in parts of Arizona and New Mexico and going into western Texas, for example. And this actually plays a huge role when it comes to severe weather and the climate there into the Great Plains in general. Meanwhile, it's flat, as we know, across the Great Plains. And it's easy for these big air masses to transport northward and southward. Northward, you get a lot of that moisture from the Gulf that will be transporting north. So it's a warm and humid environment. And then you get a cold and dry air, a lot of times that is coming down out of Canada. So it also, just the way the geography is, as you get weather makers that come over the Rocky Mountains, generally we get these storm systems that like to develop kind of on the other side of the Rocky Mountains, on the lee side of those mountains there, you get these area low pressures that develop. And just the circulation of that, it ends up pulling in all of these different air masses. And what I mean by that is you've got that cold and dry air to the north, you've got the warm and humid air from the Gulf essentially coming in, but also the hot and dry air that is out to the west. And so a way of looking at this is that you think of a warm front. We've got a warm front today in our local weather that's going to be trying to lift northward. And so out there right now, it's kind of cloudy. It's relatively cool for this time of the year. And there's a warm air on the other side of it and more humid air. And so that's trying to push this direction. So that gives you a boundary, right? So that's frequently noted there across the Great Plains as you get that warm and humid air to try to come in. The cold front, that's the dividing line between that warm and humid air, but then that cold and dry air that's coming in behind it, and that often creates thunderstorms. But then also the dry line. So this is something we're not used to as much in this part of the country at all. It hardly ever gets brought up. But in weather forecasts out in the Great Plains in Oklahoma, we talked about all the time in Arkansas when I was there, is the dry line, and this is common out there, is talking about a cold front, it is here. It's very, very similar. Now the difference is that this dry line is a separation between usually the warm and muggy air that is out ahead of it and the hot and dry air that's behind it. In fact, a lot of times the temperature may not be a whole lot different. It might be 90 degrees behind it. It might be 85 in front of it. It might actually be a little cooler in front of it, but it's just more humid. And you immediately know what side of the dry line you're on if you're out there, because it's a dry heat versus a very muggy air mass. But this dry line doesn't really move a lot. That's the difference. So if you get a strong storm system, it will pull in, the winds a lot of times will pull in that hot, dry air and will push it further to the east. But then a lot of times at night, it'll just kind of back up and move back to the west a little bit. So if you have just kind of on a general day, a lot of times that dry line is kind of in place, and it's a focus for these severe storms. And so as we go forward, there's one big event in particular where this dry line was a major factor, but it is a big factor a lot of times in the middle of Oklahoma, out towards northern Texas as kind of a focus there for severe weather. So you get these three different air masses that collide often in the middle of the country in the Great Plains, and that's our big battle zone. And that's where we get a lot of these extreme weather events. It makes it, from a meteorology standpoint, one of the more fascinating spots in the entire world. All right, so here's a look at precipitation. This is looking at a 30-year average, which is usually how meteorologists will look at the yearly normals around the country. And so you get into the blues and the greens, and that's a lot of rainfall generally. You get into the blues, you're talking over 40 inches of rain a year, close to 60, 70, 80 inches down on the Gulf Coast there. But then you get out to the Texas Panhandle, now you're down to under 16 inches and a foot of rain, and even less than that when you get out into parts of Arizona, New Mexico. So that is a huge difference right there, cutting right through basically the middle of Texas, Oklahoma, goes up into Kansas, Nebraska, and even the Dakotas. There's still a pretty big difference there. And so into the Great Plains, the average rainfall per year ranges from 12 inches to 50 inches. It's a massive difference. All right, this is a look at the probability of a tornado within a 25-mile radius, essentially. And it looks quite high all over the place when you're just kind of looking at this. We a lot of times think of Tornado Alley as just kind of this one distinct part of the country. And in all reality, we could probably draw a couple different alleys in there. One very, very notable, and the big one that we're focused on here, that runs basically North Texas right into Nebraska and then kind of tilts over a little bit into southern Minnesota. And then you have what we call Dixie Alley, which this runs right across the southern part of the country. So from Arkansas, then into Mississippi, Alabama, and that's a heightened area. Then also you can kind of see that you do have kind of an area that to the north that kind of spreads in there to Illinois and Indiana. But the big focus where we get a lot of these classic supercell thunderstorms with some of the biggest tornadoes generally are right there in the middle of the Great Plains. So Tornado Alley, that's a term that's been thrown out there. One term that probably most of you in this room have not heard of is what we call Hail Alley, and that's a real thing too. And it's usually a little farther west, but it's very notable. And so here at home, we average about 1 to 2 days a year where we're getting hail that's falling to the ground and mixing in. And so you average it out over a long term, and it's just under 2 days per year where we get at least some small hail. And usually, if we get a severe thunderstorm, we may get hail, say, 1 inch in diameter or something. It doesn't usually get too much higher than that. How many of you in this room have experienced golf ball size hail, out of curiosity? Okay, so about half, and that's pretty much what I expected. I've experienced that once in my life, and that was, in this part of the country, and that was a big, big deal. You go farther west, and you get these days with golf ball size hail are much more common. And I would suspect if we were in Oklahoma and we had the same crowd here, and I said, raise your hand if you've ever experienced golf ball size hail, I would expect probably 90% or at least 90% would be raising their hand on that. So the farther west you go, you generally, not only do we get larger hail that are mixing in with these storms, but also we're typically getting larger or more days with hail and larger hail at the same time. And so really from the eastern part of Colorado, Kansas is the bullseye there, but down in Oklahoma, and then north into the Great Plains, we get that as well. All right, what we're looking at here is we've got a graphic. We're looking at Oklahoma City, which is, again, kind of the center of the craziness generally when it comes to weather. But when you start averaging all this stuff out, the averages don't look to be extreme because we're averaging the highs and lows and all of that. But what we're looking at here is the red line is your average high temperatures you go throughout the year. And then if you look at that kind of orange bottom line there, that's the low temperature. The one in between, you're averaging it all out there. But it gets hot in the middle of the summer. I mean, routinely, they're usually dealing with highs over 90 degrees. And in the wintertime, it looks nice and comfortable with the temperature 50, but again, these are the averages. It's not uncommon for them to have highs in the 20s or highs in the 70s. I think on Christmas Day last year, it was like 80 degrees. But then, again, you can get these deep freezes and ice storms and snowstorms and so forth. But you can see the precipitation, too, which is in that darker blue shading, how it peaks in May. And May, for the southern plains, is the peak of the severe weather season. As you go into the northern Great Plains, it's June. It's usually this time of the year. And then that other curve there shows the snow. They do average snow, but it's very sporadic when it happens. You go to Wichita, and basically, so we don't have snow information on this particular graph here, but if you look at the overall picture of it, it's basically exactly like Oklahoma City, just slightly cooler. The peak of the rain is still in May, where they're averaging a little over 5 inches of rain. I mean, that's quite a bit. But then as you get into December and January and February, there's very little moisture generally that's falling. And as we continue to go northward, this is a look at Omaha, Nebraska, and it does look a little bit different. First of all, the way the scale is with the snow looks a little goofy. It's very high here, but they do get more snow. And Omaha is very similar snow-wise when you average it out to pretty much here. But again, it's usually a little more extreme typically when they typically get it. We'll get these little shots of snow here and there. Usually it'll come in a storm when it's out that way. Temperatures a little cooler in Omaha overall, especially in the winter time. You can see now those average high temperatures are closer to 30 versus 50. Meanwhile, the temperature in the summer is about the same. That's at different climate zone as we start to work our way northward, where they're getting that cooler, drier air and more of an influence there more often. They're also getting more summertime precipitation versus farther to the south. All right, so now I'm going to work our way through 4 big extreme weather events that's taking place across the Great Plains. And I tell you what, this was not easy to narrow down because, like I said, on any given week, they've got extreme weather because that's kind of a part of the weather out there. I mean, it really is a different setup. I remember going out to Arkansas, and I think it was the first month or 2 that I was there. Well, first of all, I was taken back because I'd done a show and I went to go for break and just went and grabbed some fast food or something, came back, and I'd only been working there a couple weeks, and the producer was kind of freaking out a little bit when I got back, and he's like, I think they want you to do cut-ins. And I'm like, oh my gosh, what happened, and he's like, it's snowing. I was like, okay. I mean, I went and looked at the radar. There were a few snow flurries. I'm like, yeah, that makes sense. It was in the northwest corner of the state, and they're like, yeah, they want you to do some cut-ins. This is they may have some slick roads. So it's like a different mindset for winter weather. But also when we get these cold fronts that come in, I'd never experienced anything quite like it before because temperature would be 75 degrees. You'd watch it come through. On the one side of the city, it's 75. On the other side, it's in the upper 30s, just like that. I mean, how quickly those temperatures can cool down was just very, very impressive. And this next system that I'm going to talk about goes way back, but that is very much what happened in this setup that caught so many folks off guard. So we're going to go way back to 1888. And so at that point, it's a little different getting weather information. We did have the National Weather Bureau at that time. They did archive weather maps, but again, it was much different than it is today. And so this is a look at one of those weather maps going back to January 11th, 1888, and this is at 10 p.m. And what we've got going on here, so basically you would have all of these different observations from around the country that were reported at the time. But here's a big area of low pressure coming in here. And so out ahead of it, you got high pressure over us at the time, low pressure back into Montana. And so because of how the winds rotate around high and low pressure, that pushed very strong southerly winds straight from the Gulf right into Canada. And so out ahead of that, even though it's January, those temperatures really started to warm up. And It was a brutal winter that year, but this was a great thaw that everyone was getting outside and starting to enjoy. Now, when I say thaw, we're talking like 40 to 50, topping out on the temperature. It's not like it was 70 or anything, but we all know how that is, right? I mean, if it's 40 or 45 or 50 degrees after a brutal stretch, it feels amazing outside. And so January 12th, 1888, so the following day after this weather map here, we had what was called a schoolhouse blizzard, or depending on what book and reference you look at, it was also referenced as the children's blizzard and the school children's blizzard. But unfortunately, that morning, it's still warm, and a lot of these students were heading to class, one-room schoolhouses at the time, and the weather was great. And unfortunately, the weather turned so rapidly as those kids were coming home, they were caught in that blizzard, and there were a number of them that unfortunately passed away just trying to get home from school on that particular day. So now this is going into the following morning. Here's this area low pressure that has dove here. High pressure has moved a little bit. Still a very strong southerly wind coming right out of the Gulf. So at that time, things have shifted with a lot of wind and some snow back off into Wyoming. But if you look at Nebraska and South Dakota and Minnesota, it was very, very warm at the time. So in Nebraska, the Dakotas, Minnesota, the temperature was between 30 and 50 degrees in the morning, depending on what location you were at. And the snowpack that was on the ground started to melt away. And it's like I mentioned, it was really a kind of a comfortable stretch out of what had been just a brutal stretch of winter altogether. By 3 p.m., that area low pressure has now quickly moved down to the south and east. That warm flow is over us, and everything has shifted very, very fast. And so, and unfortunately, we've got this massive, massive Arctic high pressure that was coming in behind it. And so those two systems created what we call big, big pressure gradient. That's how wind is made. Essentially, the bigger difference you have between the pressure, the more the air is going to be moving. It's going to be moving generally towards that low pressure. And so the winds were cranking up. The temperatures were plummeting because that wind is pulling in that cold air. And so by 3 p.m., all of a sudden it's totally different. Strong cold front sweeps through, gets to eastern Minnesota. The temperatures drop, and there's a massive amount of winds. This is at 10 p.m., and now the storm is already in Wisconsin. The Arctic high is here, and temperatures are just plunging very fast in the same areas that were very cold. So the storm was centered in Wisconsin. The extreme cold was sitting there into the plains. And these were some illustrations. There was all kinds of articles, newspapers, books written after the fact. There's still a lot of literature out there about this storm today. Snow totals were not overly impressive with this. In fact, a lot of the blizzards that occur, believe it or not, don't have a whole lot of snow. How many of you in this room were around here or familiar with the blizzard of 1978? And again, you don't even have to be from Ohio to be familiar with this storm, because it impacted Indiana, impacted Michigan, impacted all of Ohio. All right, that storm, I mean, it's actually difficult for a meteorologist to communicate what a blizzard is with all those memories of that storm, because that storm, when we think of blizzard, everything typically goes straight to what it was like at that point. Now, the blizzard of 78, at the time, there was a classification called a super blizzard, and it met that criteria. It had extreme cold, extreme winds, and it had a lot of snow. But blizzard has a lot more to do with wind than it does snow. And frequently, blizzards don't have a lot of snow. They have a lot of wind, and the snow on the ground, it picks it up and it moves along. And with the blizzard of 78, had all of that. I had winds gusting to 60 miles an hour. It persisted over the course of a number of days. There was already snow on the ground. Unfortunately, there was a lot of snow that fell, and all of that got whipped around and created these massive drifts. Well, there wasn't a lot of snow that fell in this particular blizzard. It was around 1 to 7 inches, depending on where you're at in the storm. But there was already a pretty decent snowpack on the ground. And when you got, in fact, there was, in many spots, 20 inches plus on the ground. So now you can start thinking of it from that perspective. All right, that's a lot of snow. 20 inches on the ground, that's like the blizzard of 78 type of snow. In fact, for some areas, that's more than what we had in 78. You go farther west, and the snow totals are more impressive with the blizzard of 78. But you start to get the picture. All right, you had some snow falling, but you had a lot on the ground. It's all getting whipped up here. And so drifts were recorded up to 30 feet high. All right, so now, if we're thinking of the blizzard of 1978, we can start to kind of see the pictures here of what this was like. Temperature dropped 60 degrees. It was about 40 in the morning, again, between 40 and 50, depending on where you were. Below zero by evening. The next morning, 10 to 30 below actual temperature, depending on location. So now when you factor in the wind chill, and the wind chill wasn't really a thing in 1888. And when we did have the scale, for a number of years, it was actually adjusted to try to make it more accurate. By the way, the wind chill itself, I should probably define that. The wind chill is a direct measurement of frostbite, is how that scale works. And so if you go out on a day where it's 0 degrees and you have exposed skin, the amount of time that it takes for you to get frostbite in that air would be equivalent to if the wind chill is 0 degrees. It should match up in theory, and there's been a lot of tests done with that. The way the old scale was done, and I believe it was refined in like 2003, if I remember right, somewhere around that point. Before that, the way the scale was done was they literally just took like a bottle of water and they were trying to like make some measurements and stuff off of that. So the new scale is much more accurate. But based off of today's scale and where those conditions would be, the wind chill would be about 50 below, just to put that in perspective. So again, you're heading out to school. I'm sure in 1888, the wardrobe options were a little different. Obviously, there were basic forecasts out talking about the storm coming in, but I'm not sure who had information to that at that point. It was very, very early into weather forecasting, and again, it was a pretty basic forecast at that. So an estimated 235 were killed, and a lot of those were children coming home from school. There's a lot of stories about teachers basically going out and survival stories and so forth. So terrible storm, and the impact that it had going all the way back, and even though it was a long time ago, I think it was definitely worthy of bringing up. Now I'm going to go much farther. I'm going to stay on the winter storm theme. I'm going to go farther south, and this is one where I have a lot of experience because I was right in the middle of this when I was in Arkansas. So this is going back to February 9th, 2011. The winter storm was the 4th that we had had in that area in 8 days. And if we were to go back and actually look at our weather records here, you'd say, well, that was a pretty rough time period for us too. It was a rough winter. There was a lot of precipitation that came, and we had those same storms that went from Arkansas all the way into Ohio. Now this last one was relatively weak in terms of what we were dealing with, low pressure and ingredients-wise. There really wasn't a lot there. With that said, there was enough on the computer modeling to where we felt like it would be a significant event. And keep in mind, I mentioned flurries sometimes would be significant for some folks. We were forecasting 5 to 10 inches. That's enough to shut things down. That's a game changer down there. You're not going anywhere with 5 to 10 inches of snow. And so that was already in the forecast. There were 2 waves. There was very high lift with this setup. And the snow ratio was a drier, fluffier snow, so it was more efficient. The atmosphere was more efficient at making snow than if it was a wetter snow there altogether. But it was a historic event, and it was kind of a surprise deal. Again, we had 5 to 10 inches of snow forecast, but it ended up being a much bigger deal than that. So a lot going on with this weather map, a lot going on, but we're just going to focus on a few things. One, you had a wave coming off of the Rocky Mountains here. And so it was almost like a clipper. A lot of times we talk about these clippers coming from the northwest, diving down. This kind of had that similar fashion where it was diving down kind of like that. You had a system coming out of Mexico into Texas that was riding right up towards us. That was kind of the main area of low pressure that we were focused on. And so this is a look at midnight here for us. And at midnight, what had happened, I was the morning meteorologist there at the time at the ABC station. We knew it was going to be a big event. It was an exhausting week already. I had woke up a little earlier than normal, so I was up around midnight on that particular day. Our chief meteorologist stayed a little later, and we agreed we'd look at the new set, the last set of model data, computer model data together, and basically kind of make the final call on the snow totals together. And we looked at it and said, yep, forecast is rock solid. Looks great. No problems with it. Felt good about it. I ended up going into work probably 2 or 3 o'clock in the morning, something along those lines. Not a lot had changed, but if we were to look at these observations now in Oklahoma, there was some very heavy snow starting to fall out ahead of this wave, and this system was getting a little bit closer, trying to kind of sneak in and merge. But again, this is all relatively weak. If we look at the air pressure with this, there wasn't a whole lot to it. From a meteorology standpoint, it was relatively weak. This is at 3 o'clock in the morning, and from my vantage point as I was driving to work, the flurry started exactly when they should have. The snow started exactly when it should have. I mean, it's always a bad sign when you've got a big weather event coming and you're ahead of schedule. I'm sitting there, forecast was done, graphics were done, and it was one of those like, that usually doesn't happen. Like I actually have spare time right now. I looked at the radar and I thought something got stuck with our graphics because it looked like it hadn't moved for a good while. So I thought, all right, maybe we lost data or something. I hit the loop and realized, no, it's working. It's just there's a narrow band of snow setting up right over us and it's not moving. So I thought, well, also a lot of the times we're working in an office with no windows. It's pretty much been the way of my whole career for whatever reason. So I went downstairs. This is on a second-story building. Went down the stairs, opened up the door. My jaw hit the floor. It had been snowing, or jaw hit the ground. It had been snowing for 1 hour, and there was a good 4 inches of snow on the ground. So I don't know if I've ever seen a snow rate any worse than that. 4 inches in 1 hour. And I opened up the door, and it's just these flakes are ginormous, just coming down to the ground. There was a photographer we had hired that was very, very nervous, did not want to be there. He was from South Carolina, didn't like snow at all. And I told him, you'll be fine, you'll be fine, you'll be fine. You'll get through it, And he was out there clearing off the vehicles, and he was not fine at that point. And I didn't really know what to say. I ran back upstairs, looked at the radar, looked at everything. And again, you're forecasting 5, 6, 7 inches of snow. It's been snowing for 1 hour. There's 4 on the ground. And it's like, all right, well, the forecast is wrong, but what do you change it to? All the computer model data was locked in. All the stuff we were looking at was kind of pointing to a simple solution there, and that obviously wasn't going to happen. Called up the National Weather Service, and I said, hey, we're right underneath that thin band. I just want to let you know it dropped 4 inches in 1 hour, and there's just silence on the other end of the line. And it's probably, we both agreed the forecast is going to be wrong, and we both agreed we weren't really sure what it was going to be adjusted to. About that time, the show's about ready to start up, and now everything that I have done up to this point is not valid, but I don't know what is valid. Facebook was very, very new at that point. I went on TV. I remember it was at 4:30 in the morning. Our show started at 5. We started at 4:30 on this particular morning. I wasn't even sure if people were up. I went on the air and said, hey, here's the deal. We're going to get more than we thought. If you right now have a snow report and you're up, send it to me. Facebook will work. Let me know your location, how much snow is on the ground. There were a lot of reports that came in. I was surprised that people were up watching at that point. And all of a sudden, you just start seeing the reports come in. And as you go back to the west under that band, it was like 6 inches, 8 inches, 10 inches, a foot of snow. When we got out to the Oklahoma border, got a report in across Oklahoma. They already had 14, 15 inches of snow. It's like, wow, this is going to be a day. So that's 3 o'clock in the morning. At 6 a.m., this was really into the peak. So we're here, and this snow icon is lit up as high as it can go. We've got this weak wave that's coming in. We've got this boundary that's set right up over us. And basically now we're having the merging of these two waves coming in. And again, even though all this was weak, we were just in that right spot or wrong spot, however you want to look at it, at that point in time. So at 6 a.m., again, we're looking at a snow rate that consistently stayed between 2 to 4 inches per hour for a number of hours there in the morning. This is a look at 9 a.m. We still had kind of this lingering situation here, and then this wave to the south that started to pull away by that time, and then by the rest of the morning, it looked a lot better. So this mega winter blast that we had, really the key was the extremely high lift. So we always look at ingredients. I always say, if you're looking at a tornado, you have to have the right ingredients there, or you're not going to get that. It's the same thing with a winter storm. You got to have the moisture, you got to have the cold air, of course, but you also have to have that lift. You got something that's pushing that air up that's going to lead to the clouds forming and the snow developing and eventually falling. And that was the thing that we had a lot of. There was a narrow zone of very high lift. So this is a look at the jet stream coming in, and it was very, very fast, but also the winds lightened up significantly as you went north of that. And so that put basically the northern part of Oklahoma through northwest Arkansas there in an extremely good position to have a very, very high lift that would be very efficient at taking the moisture we had and turning it into snow. This was the radar shot I was talking about where it came in, but that first mesoband, it was nothing to the south. It really was more like a lake effect snow band here. This is at 3:05 in the morning. This is a look at 6 a.m. So we still had this first wave and a lot of snow. Then we had kind of that second batch here try to kick in where the snow rates, as I mentioned, were right at 2 to 4 inches per hour. This is going to 8 a.m. And so by this time, all those ingredients were starting to slide off to the east through Arkansas, and it kind of went out even farther than that. But then we had this, what we call a deformation zone. This was a classic, a lot of times when you have an area low pressure move through and you get on the backside of the storm, you kind of have that trail of snow that goes through, if you've ever seen the radar. And that snow is always usually very, very efficient at producing snow. The fluffier snowflakes, it usually adds it very well. Well, that part of the storm then ends up coming in and sits right over us. So we kind of had it all from all angles. So what started as a 5 to 10 inch forecast, I was the lucky one because I was underneath of it. The National Weather Service, the other TV stations were not in my same location. And I remember one TV station went on and they had a lower snow forecast to begin with. I think it had 3 to 6 or 4 to 8. We already had over a foot of snow on the ground and they were saying 3 to 6 inches of snow. And I felt bad for them because they really had no idea. They weren't getting those reports or weren't underneath of that band. But we just kind of kept adjusting, and next thing you know, we're talking up to 2 feet of snow in the highest of this snow band, and it was very narrow. This is Fort Smith, Arkansas. This is the Oklahoma line. Coming out of Oklahoma, they had 20 to 25 inches of snow kind of in this zone. It continued into Arkansas and through the Ozarks there. But you go 30 miles north, and they had 5 inches of snow. So that 5 to 10 inches of snow actually was valid on both sides of this pretty well, but right in between, you had quite a bit. This is my house, where I think we had about 20 inches, I think, at my house there. But this became a big deal for Oklahoma. It set a state record. They had a spot that picked up 27 inches of snow out of this within 24 hours, and really it was more like 12. I mean, it all fell very quickly. Siloam Springs was our top report that we had in Arkansas, which is 24 and a half inches of snow. And we missed the state record in Arkansas by ½ inch. So we almost set 2 state records out of that in terms of the snow. But we were not done because we got more surprises the next morning. Because now this big Arctic high was sitting right on top of us. And so the following morning, the temperature dropped to 31 below into northeast Oklahoma, and that was a new state record. The temperature at our airport, next to where the station was at 21 below that morning. Fell short of the record, which was at 29 below. So that is, to put that in perspective, Toledo's all-time coldest temperature recorded is 20 below zero. And here we are, 10, 11 degrees colder than that in Oklahoma, and even colder than that in Arkansas. And so to this day, the biggest snowstorm and the biggest cold blast that I've experienced was within 1 day of each other with this storm in Arkansas. I could go on about other stories, the biggest ice storm I've experienced, the biggest severe weather outbreaks, all of that. We're also down in that area. So again, a very extreme part of the country, and certainly that's a good example of it. All right, 2 other events, and I'm going to focus the severe weather. We're going to talk about, and again, this was very tough because, again, you could look at a number of tornado outbreaks. We're going to go to May 3rd, 1999 with this one, right into the middle of Oklahoma and also southern Kansas. 72 tornadoes, 664 people were injured, 40 killed. 33 of those tornadoes were F0s, and that's typically how it is. Usually, if you get, most of your tornadoes are either F0 or EF0 or EF1s at this point, and the farther up that scale you go, the more and more rare they are. It is very rare to have an EF3, 4, or 5, especially a 5. Many times the country will go 2 or 3 years and we won't even record one. But this snapshot here in particular was that F5 at the time. By the way, the scale also changed like around 2005. Not really changed, it's just they updated it. So before that point, we say F, and then after that point, it's EF, which is called for the Enhanced Fujita scale. So that's the only difference there, but they are comparable with one another. So again, going back to the climate zone, right in the middle of Oklahoma going into Kansas. Usually, I mean, this is really the big part of the battle zone, but that's also where we have that dry line that is a big focus. This looks like a mess, this map, I realize that. But what we had was we had a lot of wind shear. So we had this jet stream diving straight down and then cutting right into Oklahoma. And what we had also is what we call a negatively tilted trough. Basically what happens is that the way the cold air comes in, it was able to come in and then start to kind of curve underneath of the storm system. And so what that does is that means now Aloft, if you kind of look at the elevation of a storm, you have hot and humid air right at the ground, but that cold air gets pushed out ahead of that, and now you've got cold air essentially sitting over the top of very hot and humid air. And so that makes the instability grow much, much higher. So it makes it much more volatile. So that situation was present, but also there was just a lot of wind shear, but that dry line was right here. And that ends up becoming the focus here for those storms. So basically we had the collision of 3 different air masses, just like I was talking about that is typical with the climate there. We had the negatively tilted trough to put the cold air over the warm surface, and also that Gulf moisture flowed right into central Oklahoma and Kansas. So there was no shortage of that. Very high wind shear, 80 mile per hour jet stream over the panhandle there of Oklahoma going into Texas. 80 mile per hour winds, a low level jet that's about 4,500 feet above the ground. That was at 45 miles an hour. That's from the south to southwest, but the ground wind was out of the south to southeast. And so that is the classic wind shear, to where those winds at the ground are south-southeast, but as you go up, it tilts with height. And so now what that does, and the winds are stronger with height, so as the storm goes up, the winds will kind of tilt it over a little bit. The heavy rain will fall in a different part of the storm than the fuel that is going up into it. And so now when that happens, this storm can live a lot longer, and it has the potential of becoming severe. If you have these summertime showers with no wind shear, you get the heat and humidity, the storm cloud goes straight up, it starts raining, and the cold air comes right down on its fuel source, it collapses, it's done. And then, 15, 20 minutes later, another cloud will form, and that just continues to repeat. But with this setup, these storms can last a long time. And then when you have that twisting with height, now those storms can begin to rotate the entire thunderstorm. And so that's exactly what was going on with this setup. Here's a look. There's a lot of different things going on here. If we're just looking at kind of these winds, and we have the same thing here, this is what we call a sounding. It's measuring a lot of data as you go up with height, but it's measuring the winds. So at the ground, there's your south to southeast wind, and you can see how it turns as you go up. And eventually it's more out of the west as you go up. You can see that over here, to where this is more out of the west, but at the ground it's more south to southeast. And so that allows that storm to begin to tilt and twist. And so that became very evident, these monster supercells growing on the satellite picture. Here's your dry line coming in, and these overshooting tops are the most powerful storms there. So this is getting into the evening hours. I mean, that thunderstorm in particular, just very, very impressive. So the Storm Prediction Center, the National Weather Service, were tracking multiple tornadoes at the same time from Oklahoma into Kansas, with a lot of supercell thunderstorms in the late afternoon and evening. So each of these storms that we're developing were beginning to just rotate. So there's one, there's another. And even these up here that don't look as intense became tornadic and continued to develop as they went along. This was the worst of it, the F5 that I mentioned, and unfortunately, here's your tornado that was associated with it. So here's your supercell storm. The bottom, it's basically southeast corner there of the storm, or southwest corner of the storm, rather, is where you get that tornado develop. There's your rotation that's inside that storm. And unfortunately, this thing had a track where it took it right into Oklahoma City. So now you're talking worst case scenario, high-end, large damaging tornado going into the metro area at the evening time when there's a lot of people out and about. Tornado was about a mile wide. It traveled 38 miles in length. It was strong enough to peel up asphalt from the roads. It's never a good sign when that happens. Usually you're talking an EF4 or 5 at that point. And also, this just blew me away. Toss an 18-ton train car 3/4 of a mile. So, I mean, it was just constantly kind of pushing it and dragging it, but it ended up 3/4 of a mile away from where it originated there. $1 billion in damage, which would be about $2 billion in today's money. And this was from 3:30 p.m. to 4:51 p.m., went through the Oklahoma City metro area, as I mentioned, killed 36, 5 other deaths that were indirect, so illnesses and accidents that were indirectly caused from the storm. 583 people injured, and 2,500 homes that were damaged, and 1,800 that were completely wiped out there. So these are some of the images from that time frame. Complete devastation. And I remember seeing the headlines. I think it was on a USA Today, and I still have those images. I mean, at that point, I remember I think that was kind of the first time where I'd ever seen anything quite like it. And I remember just taking all those articles and really trying to learn and understand more about it. So this definitely had an impact on me too, even growing up 1,000 miles away. Here's a look at the map with the tornado tracks. Again, here's the metro of Oklahoma City. This was the supercell that turned into the F5. It was an F5 here, it recycled. It also reached F5 again there, kind of on the southern part of Oklahoma City. Ended up still is an F4 as it went through Tinker Air Force Base there. And so here's more, here's the downtown part of Oklahoma City, and then here's Wichita. There was an F4 tornado as well that went through Wichita. So you had an F5 hit Oklahoma City, an F4 hit Wichita that day, and then an F1 that hit Tulsa. So just not only a horrible day in terms of tornadoes, but just where they were hitting to in these big population zones. So this is more of a zoomed in look to Oklahoma City. And again, here's that monster tornado. But then, I mean, you had two separate tornado tracks up here north of Oklahoma City that were almost right on top of each other there as well. So definitely a lot going on. This is another look at what was happening and kind of more of a simple weather map. Here's the cold front, here's your cool dry air, here's the warm moist air coming from the Gulf, here is that hot dry air that was getting pulled in from the desert. We call this the triple point where all of those come in and meet. So basically this dry line responsible for a lot of those storms, kicking those off, and then the triple point was up by Wichita where they had that F4 tornado go in. This was a look at, as we go into the final event that I'm going to talk about here, is we're talking about 2011. Again, I just talked about 2011 in terms of a snowstorm. Back in February, 2011 was the most extreme weather year that I've ever witnessed, and I don't know if I'll ever see anything quite like it again. And part of it was because of the year, part of it was the pattern we were in, and the other part was my location, which again was in northwest Arkansas at the time. So this is, we're talking about the Joplin tornado, is what we're talking about. And while Joplin was a little farther north where I was, we were neighboring markets. So Joplin was like one county north of where my viewing area ended. And this was on a Sunday night. And I mean, it was a very busy night for us. I mean, I was focused on what was happening for us because I knew that we had a chance of severe weather and tornadoes itself. The initial outlook from the Storm Prediction Center is labeled here. This is a look at the outlook, which is more basic than you had a slight, you had a moderate, and you had a high. So there were three categories essentially. And where Oklahoma, Arkansas, going through parts of Missouri was in that moderate risk there. This is the actual tornado risk, which showed 10% chance for tornadoes. How that works is a 10% chance of a tornado developing within a 25-mile area. That's what that percentage means. So it's kind of hard to conceptualize. I mean, even for myself, where I'm dealing with data and numbers and maps on a daily basis. But 10% is an elevated risk for tornadoes. It gets your attention for sure when you see something like that. The hatched area here is also an indication that those tornadoes had the potential of being longer lived and stronger, meaning F2 or EF2 and stronger there. So this is another way of kind of looking at the potential for a tornado. We're looking at an indice here that is trying to measure the significance of a tornado, how likely it is for a tornado to occur, but then also how strong it could become. And so this is where I was at the time, and my forecast area went into Missouri, went out like this into Oklahoma, and went all the way down like that. So when I come into work and I'm looking at that, I'm thinking it's going to be probably a pretty rough day for where I was at. Joplin is still in the higher area here, but it's just a little bit farther to the north of it overall. This is a look at the Joplin tornado and its path as it went through the city in a timeline. Again, this was a Sunday evening, 5:41 p.m., running all the way to about 6 p.m. And this is another example, just like Oklahoma City. I mean, you had an EF5 cut right through a massive population center. And while it wasn't during the week, it was still around the same time there in the evening hours. There's a lot of people out, and you can see how this tornado cut that path through. A lot of information on this, but I just kind of want to show the overview and that timing. This was very unusual and a clear signal on radar that not only was there a possibility of tornado, but there was one occurring. the shear, or the rotation inside the storm was off the charts, as extreme as probably any of us have ever seen it. But then also at the same time, it literally was showing debris, like a 3D scans were showing debris being lofted up into the storm. And that is not a normal thing at all. Oftentimes, even when you have tornadoes, you're not seeing anything quite to that extent. But yeah, that's what the radar was showing at that time. And as we take a look, initially it was very bizarre, because I remember watching this on radar and said, this is a storm like I haven't really seen before. You had a supercell develop. Here's eventually where it was going, but you had this guy out to the west, it had rotation with it. This had rotation. There was rotation up here. All of these cells just started kind of merging together. And even as they were merging together, there was high shear, lots of rotation, but there were a lot of different points where it was happening. And so it was kind of difficult to even understand how, or where the greatest threat was. But eventually this all merged. All of these cells merged into one gigantic supercell. And basically here it is, but it rotated around so much that this curl right there, that's where that tornado was, as it went right through Joplin. So initially, I mean, there were tornado warnings that were issued, there was a lot of rotation, but then all of a sudden, it was like, it just all erupted and at the wrong time as it was going through the city. So timing here, as I mentioned, about 5:30 to 6 o'clock roughly, so it was EF5 over 200 mile per hour winds. And the length was shorter than the one that went through Oklahoma City at 22.1 miles, although the storm was a little slower moving as well. The width also a mile wide there, killed 158, injured over 1,000, homes destroyed over 7,000, costliest tornado in U.S. history, $2.8 billion today would be over $4 billion. And here's I'm going to show a couple images here with the rotation. So that's that same image. Here's Joplin. Here's where that tornado was. I know for a lot of you, you're looking at just different colors, and it's hard to conceptualize what's going on here. But basically, these colors are so twisted, it's off the charts. It was at a level to where we essentially almost never see it, and it was all happening there. And looking back on the storm, I saw the tornado warnings, I saw the rotation, it was like, well, that's bad. But the timing there was approaching 6 p.m. I had a show at 6 p.m. And so yeah, we showed, hey, there's a tornado warning up there. It doesn't look good. But at the same time, we had some other storms starting to develop that were moving our way. And there was a watch box that got put out, and there were warnings. And we ended up going, our county that I was in for the station went under 7 tornado warnings on that night. Everything was kind of a blur. My assistant news director at some point, so basically my boss, came in on the weekend, and we got all this stuff going on. We got these tornado warnings starting to pop. We got all this severe weather locally, and he comes in, he goes, what do you know about Joplin? Well, at that point, I had no idea. All I knew is what I was looking at radar. I hadn't heard any reports. I wasn't even sure. I mean, looking at the data, I was sure there was a tornado, but I had no idea to what extent, where it was at, how people were impacted, none of it. And so I kind of got a little upset at the time. I mean, looking back at it, I was like, wow, that was, I had no perspective on it. But my response back was, I'm not focused on Joplin right now. Look at all the stuff that we've got going on right now in our area. And he's like, well, we need to know because we're sending somebody up there. And I was like, what about here? What about our local area? We're going to have tornadoes tonight probably in our area. And he's just like, okay, well, he just kind of walked out, and I continued to cover everything. And it wasn't for a couple more hours. It wasn't until we actually got somebody up there, and they were able to get a live shot, and they started sending it down, and then I just could not believe what they were dealing with up there. And so they were stationed at the time outside this hospital that was just completely in rubble, and they started to hear the stories, and we all remember the national coverage of that. I mean, every news outlet in the country was getting a flight there and flying in. Has anybody seen the Netflix documentary on the Joplin tornado? Okay. I mean, it's terrifying. I mean, that documentary is absolutely terrifying. So it is something that, I don't know if I recommend it or not because of that. I mean, it's very real, it's very raw, but it's just mind-blowing, what these folks had to go through. And they go through these personal stories, and it is just something else. So this was a look at basically the images here that we had, this is a look at essentially the timeline. I mentioned there was a lot of rotation, there's a lot of stuff happening. So there were tornado warnings issued for a long time. In fact, there was questions about this on whether maybe the warning was too good. And what I mean by that is that there were tornado warnings issued way out ahead of this. Again, there was all this rotation. It recycled. It's merging in with other cells. They continue to issue these tornado warnings. And so you had a ton of time. I think like more than a half hour's worth of time. And there were people that went into their safe spots and were like, well, nothing's happening, and then came out and got hit. And so that started a big debate in the meteorology community of like, well, was the warning too much? Was it too good? How do we do this in the future as technology continues to get better? Because if you warn somebody an hour ahead of time and they go to their safe spot, well, are they going to come out of their safe spot about the time this tornado comes in? And so that debate continues today on what that looks like down the road as we hope that these tornado warnings and the technology continues to get better and better. But it is really something from it all together. This is a look at all the tornadoes, and it wasn't just Joplin. Joplin's right here. That's what went through. We had all the tornadoes in our area too. And then you look to the north, and these are areas that didn't have as high of a risk there, but there were 75 tornado reports on this given day, hundreds of wind reports and hail reports that were scattered all across the region too. And some of those reports got all the way up until the Indiana border there. But nearly 1,000 severe weather reports in total, again, 75 tornado reports altogether. And this was a much bigger deal. And so this other event, no way it was going to make the cut, but from a personal reflection, this happened, all the focus was on that. Meanwhile, this was not the only severe weather event we had that was coming up. It was either 2 days or 3 days later into the week, in the middle of that coming week, we had a high risk out for severe weather. And the setup actually looked worse than what it was for Joplin. So if you do remember some of those reports, as they're doing reports about the cleanup and everything else, and a couple days later they're saying, and there's another threat of severe storms today, that was that event, but it was focused a little farther south. And this one, for me personally, was the biggest severe weather event of my entire career. These big supercells were developing. They cut right through our area. They developed off the dry line by the time they got to us in eastern Oklahoma and western Arkansas. It was about 11 p.m. To midnight and going into the early morning hours. And we had a few people that died on that particular night. We had it was an EF4. I think if it would have probably hit a bigger structure, it may have been an EF5. I mean, it was at that caliber, but it went about 45 miles wide. And I will never forget, we got a message from the National Weather Service in a chat program that we're in. And usually it's like, there's a good chance there's a tornado, or we're seeing this detection, or whatever it may be. But he sent a message, not we believe there's a tornado. He said, this tornado is more than a mile wide, and sure enough, that was about 1.25 miles wide. And I remember driving through that damage path afterwards, and you got into the middle of it, and it just, everything had wiped out as far as you could see. So that wraps up my presentation here, talking about the climate in the plains and all the different weather events. I want to leave the rest of the time up to you guys for whatever questions come your way.
So the Central Plains have this very severe weather. In your opinion, what parts of the country have the least severe weather, where I want to live?
Yeah, that's a good question. So there's a few different ways of answering that, because when you think of like severe, I feel like every place has their thing, right? California doesn't typically get severe weather, but they get earthquakes, they get mudslides, they get other things that are problematic. But if we're just looking at like severe weather in general, basically the more away from the middle of the country you get generally is better. You get out into the mountains, it's not as bad. The Pacific Northwest is usually tame. A lot of times New England's not bad either. So the farther east you go, it gets a little better. It's funny because I think there's a couple of you that were in here a couple weeks back. I gave a presentation on Hawaii and Alaska, and I talked about all the wild weather that they can get with the big extremes, but they don't really get severe weather that often. It's usually very tame in that category. In fact, Alaska, it's very unusual to get that type of weather. So Yeah, it's and what we get in the Great Plains is there are a few other spots around the world. Like you get in Italy, they have some severe weather occasionally. There's parts of Brazil that will, but like it is nothing that compares with the Great Plains. I mean, that really is one of the most extreme, but also one of the most tornadic areas of the entire world. Actually, it is the most tornadic area of the entire world. So it is very unique in that way.
You mentioned that the technology is getting better and
Yeah.
better. How are you using AI in your weather forecasting, and how do you see it affecting that whole field in the future?
Yeah, so that's $1 million question. It's easy to explain how we're using it right now. It is a little tougher to figure out where we're going. I mean, we're having this conversation all the time. So as of right now, AI, we have, well, there are more than 2 computer models out there, but there is, like Google has a model that is trying to really focus in on hurricanes, and it has shown some success. So last year it did pretty good. Last year it seemed to do a little better than some of our traditional models. Now it's only really plotting kind of the center and the strength and where that's going, and they're not really focusing in on much else beyond that. But it is a tool that can help us right now for hurricanes, and I suspect it's only going to get better from there. For me, on a daily basis, we have 2 AI computer models that we'll take a look at. Last year in the summertime was about the first time we've had them for a few years, and they've been terrible. I mean, it's one of those things you look at them, you're trying to get familiar with it because you think in the future that this will be a tool that will be more useful, but up to that point, it wasn't something that was going to really help you with the forecast. Starting last summer, they updated one of the computer models, and this was the one out of Europe. So the European Union runs some computer models. If you ever hear a meteorologist talk about the Euro computer model or something along those lines, they're talking about the global model that is being run out of the European Union. And it's a very, very good computer model. We have one in the United States. Canada has one as well. And there are a couple others, but they're not as good. So those are the 3 kind of top global models. Well, Europe decided, hey, we're going to run a global AI model. And America was like, oh, we need to catch up. And so they started to run one as well. But the European AI computer model, last summer, we started to notice it came out and it was much better than what it was before. Now, it's not great at all right now when it comes to severe storms. In fact, I mean, today's a perfect example. It's had rain, but it really can't tell you much more than that. But where it's good with is that it seems to have a strength with pattern recognition, and I guess AI in general, this is kind of a strength, right? It is looking at all of this data, it's looking at patterns, and then it's kind of looking at where we are, and then it's trying to say, okay, well, if we're here and we have these patterns now, it likely will transition to this. And that's really the one area where it's doing better than anything else. So perfect example is that AI European computer model, like day 4 through 10, kind of in that range, does pretty good now picking up on like the overall pattern across the country. And a perfect example is that 10 days ago, a week and a half ago, when we were looking far out, all of the computer models had us blazingly hot right now. But the AI European model in particular did not. It had us cool and it had the heat dome going way out west. Well, that's exactly what happened. So that's like its strength, but it hasn't been able to tell us a whole lot other than that. So we're getting there, I guess is what I'm trying to say. And I look at it a lot for the long range forecast because it does seem like if we're, say, a week out and the AI is showing one solution and everything else is showing the other stuff, I'm very cautious to rule out the AI because a lot of times it ends up becoming right a day or 2 before everything else. So that's where it's helping right now. America's doing its best to try to catch up, but I'm just being honest, I don't trust that one model at all. It seems to be the worst out of all the models that we have right now when it comes to the AI stuff. I'm sure it'll only get better from there. Now, where it goes from here is a great question. I don't know if it'll ever be able to completely replace the physics that are based in the models we have now, but I can only see it getting better. I can't see it getting worse. And so I do think it will be a tool that will be useful down the line, and I'm excited to see where it goes, especially with some of the progress in the long-range stuff. I'm excited. I'm excited about the future to see where it goes with all that. But there's a part of me that's very cautious to jump on the train that this is going to solve all of our problems because I don't think it will. So I'm really kind of middle of the road on it, if that makes sense. But there's a lot we don't know. I have no idea where we're going to be in 5 years with it, let alone, say, 10 years down the road.
So I guess my question is, Tornado Alley has been pretty much what you've been describing,
Yeah.
but there's been a lot more activity further to the east.
Yep.
Would you say Tornado Alley is expanding or moving to the east?
Yeah, so it's hard to tell if okay, well, let me go back to what you were saying. There's no doubt that, say, over like the last really 30 years, we've seen a shift. We're still seeing those tornadoes in Tornado Alley, but there's been quite a bit of data to show that, especially like Dixie Alley in the south, there are definitely more tornadoes there than what there, say, was the 30 years before that. So then the big question becomes, is that a shift? Is that like a climate thing where this is now beginning to evolve? Or is it a phase? And that one's really tough to solve, because tornadoes are a type of data where it's so chaotic. And what I mean by that is that you get one great big event, right, that I was just showing here, where we had 75 tornado reports in a day. But then you might go weeks and only have a handful of tornadoes in that same time period because the ingredients aren't right. So it's like when it happens, you get a lot of it and then it backs off. And so when you look at the data of like, okay, trying to figure it out and average it out and try to figure out trends, you don't have a whole lot of confidence in the data because it's so chaotic when you look at any individual time period. And so that makes it very difficult to look and see how things will adjust as we go forward. The other thing is too, we really don't have great data beyond like the last 40 to 50 years. We've got data in the 50s and 60s, we've got it before that, but it's really only the big tornadoes, and we don't have a lot of the little ones that have been included with the records, and so it's without that lack of data, it's kind of hard to tell for sure. I think there is an argument to make that either there's expansion to the east or the focus of Tornado Alley is shifting east just a little bit. For this reason, because when we look at the climate of the country and we see how things are evolving and changing, what we see is generally the eastern part of the country is becoming wetter, more humid, and we're seeing that the western part of the country is becoming a little bit drier. And when you look at those locations, the drier areas also includes kind of in the middle of the plains. And so because of that, there is reason to believe in theories that things are shifting because of just an overall climate shift. But it's tough to tell. It really is tough to tell between whether it's a phase or a permanent shift that's happening.
Could you go back to earlier, the first couple frames?
Yeah.
Are
you talking about like the climate here?
Yeah, the one before that.
Okay.
That's fine right there, yeah.
Okay.
So we're hearing a lot about El Nino being a super El Nino.
Yeah.
And so one question is, how does that look in the near future? And a second question is, with global warming in
Yeah.
general, how these two factors might affect things in the future?
Yeah, so let's start off with El Nino. So El Nino itself so we are rapidly making a change now. So officially we have reached El Nino territory. El Nino is the above normal water temperatures in the equatorial Pacific, and once you get to a 0.5 degrees Celsius or higher, kind of as an average in that basin, that's when you reach El Nino status. If it's a 0.5 degrees Celsius colder or lower, it's a La Nina. And we've been in off and on more of a La Nina a little more often here the last few years. But now, not only are we flipping to an El Nino, which we're there now, but it's a weak one right now. It does look like it's going to continue to rapidly develop. All of the modeling shows that. And by winter, it's likely to be strong, possibly very strong. Very strong also could be, you could use the term super El Nino. At that point, now you're talking more than 2 degrees above, 2 degrees Celsius above normal compared to what it typically is. So what that basically does is that is now going to set off, it alters the jet stream, and then it sets off a domino effect that just kind of triggers all the way down the world. And so there are still other factors that get thrown into it. It's not just El Nino controls everything. It's El Nino plus everything else on top of it. So going into the winter season, that jet stream typically it is more in the southern part of the country. So the southern part of the country is very wet usually, but because the jet stream leaves this part of the U.S., we typically are drier, and also we typically warm up. So an El Nino winter, well, let me back up. For summer, it usually does not have much of an impact on us. El Nino is good news for Florida for the hurricane season, and it's good news for the East Coast, because what it does is it creates more wind shear into the Atlantic and causes less in the Pacific. So the Pacific typically has more of an active hurricane season, but again, that doesn't usually have an impact on the United States. It's the Atlantic hurricane season that usually has a big impact. And with more shear there, usually you have a less hurricanes developing altogether that are around. So that could be good news, although locally for us in the summer, it usually doesn't have much of an impact either way. Fall, it starts to warm us up and dry us out a bit, and winter is usually the peak, and that's also the peak of this El Nino that is anticipated. And so right now, there are all indications which suggest that it would be a warmer and drier winter coming up this winter than normal. So that's how it would impact us in the Great Lakes. It's usually, basically it's a split jet stream. The subtropical jet's down here where it's really wet. The Arctic jet is farther north, that's why we're warmer. As for global warming and climate change and how all of that kind of plays in, so what we're seeing across the country is, believe it or not, we're seeing less impact here than pretty much the entire US. You look at like how the temperatures are changing and the impacts, and you get into basically the Midwest and the Great Lakes, and we're still warming up and we're getting more moisture. That's kind of our biggest thing, is we're getting more humidity and we're getting a little more precipitation overall over the long term. But we're not seeing major temperature fluctuations, and what we're seeing is typically overnight lows are coming up because of the extra humidity. Out west is heating up a lot, and they're becoming hotter and drier. It is becoming more muggy and wetter here across the eastern part of the country, and again, once you get to the coast, it seems like there's a little more of an impact altogether. Hopefully that answered both of those questions.
When we talk about tornadoes,
Yeah.
I mean, they talk about the ones that go in the ground and go for miles.
Yeah.
Is it common? We had one in Edgerton, Ohio, 2008, 2010, somewhere in there, where the tornado just dropped basically down on
Yeah.
one big building and bounced right back up. I mean, it was maybe 100 feet long. It took a little bit of roof off the building here, then it just tore the town hall apart, the old
Yeah.
town hall. A little bit off the building across the other street, and it popped up. It did no more damage. Is that common, or is that really weird?
What you described is normal. That happens, I mean, probably somewhere around 90% of the time.
More that way than the ones that
Oh,
go on ground.
absolutely,
I was just
absolutely.
curious about that.
Yeah, it's one of those deals where it's like, I want to say like 90% of the tornadoes are like EF zeros or ones. When you start getting to a 2, that's the thing too. It's like, maybe it's 85%. I'm trying to remember the exact number, because we talked about this even on TV within the last couple of years, because we had an EF2 go through somewhere down in like Hancock County or somewhere around that area, and it did some damage. Maybe it injured like one person, but it definitely tore a lot of stuff up. And so I was trying to describe like, yeah, it's an EF2. You think like, oh, it's not a big one. No, it is. Like, you get to EF2 and stronger. Those are rare, and those are considered strong tornadoes. I mean, I know every tornado is strong, or else, it wouldn't be a tornado, I guess. But you get to EF2 and stronger, I mean, those are very rare, and those are the ones that will stay on the ground for many minutes at a time, and definitely will do a lot more damage. But what you described, that's what happens most of the time. It comes down, does a little bit of damage, goes up, or it'll recycle, and maybe it happens again or something along those lines.
Much is your ability to forecast tornadoes and the path that they'll take? How much over your career has the ability to forecast tornadoes and the paths they'll take improved?
Yeah. So forecasting tornadoes, beforehand, so like, okay, today, I'll use today as an example. So today, We've got some light rain that's coming in. We have a severe threat coming up later on tonight, and we're hoping the instability stays low enough to where we don't have a whole lot of issues overall. It definitely looks like as you get like to southern Indiana, they're going to be dealing with a lot more problems than us. But so we'll use today as an example. As we've been looking out ahead, it's like, okay, so we've got the ingredients that are there, and you're looking at how the fronts will move through and kind of where the storms will line up to see kind of what the probability would be for tornado and severe weather in general. And that's pretty much all we can do ahead of time. There really isn't much more we can do, and that, while it's getting better with the modeling with some of our high resolution stuff is definitely improving when these storms will initiate, when they'll develop, when they're going to be coming through, and how they'll track generally. They have gotten a lot better over the 20 years plus that I've been doing this. But we still can't, and we've also gotten to a point where these computer models will pretty much detect or predict tornadoes, but they're not right. We're not going to show that. Like, they'll show these rotating updrafts and kind of where they go through. So that gives us a good idea of like, okay, the model is seeing these ingredients come together to the point to where it is producing stuff, but there's no accuracy at all if you look at like, okay, it's got a rotating updraft going through whatever city. Absolutely no ability to forecast individual tracks on that. So it's definitely gotten a lot better kind of overall forecasting severe weather, looking at how the storms will track and so forth. But ahead of time, we can't forecast a tornado and where it'll develop. Now, during a tornado warning, as you get these storms that develop, you start seeing the rotation, that's a different story because now you can get a better idea of, okay, you've got the supercell, the tornado generally is going to move at the same speed and path as a storm. And so at that point, you can get a pretty good idea of where it's going to go and so forth. But I don't know if it's improved drastically, that part of it. We're getting better lead time, better warning time. We're getting a better ability to forecast, like today, 8, 9, 10 o'clock tonight, it looks like that'll be an active time period. And we have more confidence in that to where 20 years ago it was like, well, we got a chance somewhere between tonight and early tomorrow morning. So all of that's getting better, but when looking at Doppler radar itself, I don't know if we've really seen a huge adjustment on like the actual track, as you're kind of doing real-time storm chasing. I mean, what really changed all of that was Doppler radar. I mean, that changed everything when it came to tornadoes and getting warning and lead time and all of that. I mean, it's hard to understate, I guess, how significant of an impact Doppler radar has made in all of our lives when it comes to not just rain, but having that warning and that ability to know ahead of time, which is pretty incredible.
Oh, Marcia.
Thanks for giving me a second shot, John. So in terms of your career, I heard you mention studying physics.
Yeah.
Could you talk about how you become a meteorologist, and do you see, or are there already industries that are hiring meteorologists just to do very specific forecasting for them using some of those models that you're talking
Yeah.
about? So you're, on a very traditional TV, that one we understand, we know, everyone knows.
Right.
But what else can you do with a meteorology career?
Yeah, so meteorology takes, well, first and foremost, it's a lot of math. I mean, the math then leads into the chemistry and the physics and all of that. But I think that's the biggest thing that a lot of people, especially younger folks, or even myself, when I was looking at getting into the career, I'm like, okay, yeah, you got to be good. You have to be good at math. And I was like, oh, I'm good at math. This will be fine. And then I got to college, and I'm like, oh my gosh, this is a whole different level of math. There's calculus 1, 2, 3, 4, and then differential equations beyond that. And so that was a big wake-up call. And so the advice I give anyone, especially younger folks that are trying to figure out like, maybe this is something I want to do, I just say when you get to middle school, junior high, but especially high school, like take as much math as you can. Like take as much as you can, because that will ultimately help you significantly when you get to college. It'll help you in your math classes. It'll help you in all of your science classes. And yeah, there are some pretty tough courses to get through, for sure. But then beyond that, you get into your meteorology classes, and those are tough too. But for me, once I got to that point, it was like, I'm using my brain. It's not easy and everything else, but I just loved it. So it was a lot different at that point. So yeah, for me, it's been kind of the traditional TV route. The other very traditional route is working for the National Weather Service. So kind of similar to TV, you've just got these Weather Service offices scattered all across the country. And so they're launching weather balloons. They are looking at computer modeling, they're forecasting. They're the ones issuing tornado warnings and all the warnings that we see. And so they're doing a lot of stuff that is very, very valuable. A little more kind of behind the scenes with that career. You have more specialized areas like the hurricane hunters with the Hurricane Center, which is, it's a very specific deal where they're flying into a hurricane and so forth. A lot of people think storm chasing is like a career path. For 99% of them, it's not. It's something that they're just very passionate about doing and kind of do for a time period. There's research, so there's teaching, there's research opportunities. And without these guys, our computer models would never get better, and none of this would get better. And so that's what keeps things moving along and improving everything altogether. But you also mentioned our companies hiring meteorologists to do specific work, and they are. It depends on the company. Usually they're large companies, but like airlines, but also like UPS and FedEx and so forth. Energy companies is another one. Sometimes it's specifically for weather and trying to get people deployed in the right spots if there's a high wind event. But also out west, it's a lot about fire weather. They are really trying to figure out, okay, at what point do we need to alter our plan and try to figure out how to deal with that. So yeah, there's a variety of spots there, and there's meteorology consulting. There's AccuWeather, there's a big private company that has a bunch of forecasters that they'll do different stuff throughout the country as well, all across the country. And so there's a lot of different things involved with it.
Thank you very much, Ross.
Yeah, no
Thank
problem.
you.